Hello everyone, welcome to the session of Design of Machine Elements 1. So in the previous session, we have taken a problem of complete design of screw jack. In the previous session, we have completed design of screw rod as well as the nut. So this will be the problem if you remember. So the problem is design a screw jack with a lift of 300 millimeter to lift a load of 50 kilonewton. Select C40 steel for the screw material. For that they are given sigma y value. Then soft phosphorus bronze for the nut material. For that they are given sigma ultimate and sigma y value. So this will be the given problem. Based on this we are extracted the data. Then we are also completed design of screw rod as well as the nut. From the design of screw rod what we got? So allowable stress, that is allowable stress of the screw material 109.53, then allowable shear stress is 54.76, then standard core area is 616 millimeter square, major diameter of the screw is 34 mm, minor diameter of the screw is 28 mm, pitch value is 6 mm, then major diameter of the nut is 34.5 mm, then mean diameter of the screw is 31 mm, then coefficient of friction, that is tan phi, which is equal to F, which is given by 0.14. Then from inclined line concept, tan alpha, which is given by 0.0616. This will be from the design of screw. Now from the design of nut, then what we got? The allowable stress in tension, that is 39.42 megapascal, allowable stress in compression, which is 57.5 megapascal, allowable shear stress, which is 19.71 megapascal. Then what we got? Then number of threads in the nut, that is 14, then length of the nut 84 mm, then thickness of the nut flange, that is 16 mm, then diameter, outside diameter of the nut is 53 mm, diameter of the nut at flange, this one D2, diameter of the nut at flange, that is 63 mm, then finally length of the screw. So once you calculated the length of the nut, length of the screw, which is given by lift, that is 300 mm, plus length of the nut, that is 84 mm, plus margin of 15 millimeter. If you going to calculate this, then you will get 399 millimeter. So in the step 1 we design for the screw rod, in the step 2 we design for the nut, as well as we check the induced stress in the screw as well as the nut which is within the permissible limit or allowable limit of the materials. So from that we concluded that design of nut as well as the design of screw rod both are safe. Now we move on to the design of next part, that is design of screw head or collar. Design of screw head or collar. You can see here, this will be the screw rod, this will be the nut, both this design is over. Now I am going to design this screw head or what we call as collar. So in this, if you can see this, so this will be the screw head or collar, this will be the screw rod. What we need to calculate while designing a collar or screw head, that is what we need to calculate, height of the collar, that is H1, height of the collar, this one, then outside diameter of the collar, DC0, this one, from ear to ear, outside diameter of the collar, DC0, then diameter of the pin head, this one. So I need to calculate this diameter, capital D, then mean diameter of the collar. So once you calculate DC0 and D, so by taking mean of these two values you will get the mean diameter. So we need to calculate these things. Now height of the collar, which is approximately equal to 1.5 times of D. 1.5 times of D, that is the value of H1, DC0 and D, all these with respect to the screw rod. That means we are going to calculate the H1, DC0 and D, so with proportionals with the values of screw rod. Now H1 which is given by 1.5 times of D, that is major diameter of the screw. If you are going to calculate this, that is 1.5 times of D. D value, major diameter of the screw, is how much? 34 millimeter. So 34, once you calculate this, then you will get H1 that is equal to 51 millimeter. The height of the screw head or collar, which is equal to 51 millimeter. Now outside diameter of the collar, this one, I need this value. So which is given by 2 times of D, that is 2 times of major diameter of the screw. So which is given by DC naught, 2 times of D is 34 mm, which is given by 68 millimeter. DC naught which is equal to 68 millimeter. Then diameter of the pin head. So I need to calculate this diameter, so which is given by capital D, which is also equal to inside diameter, which is also given by DCI, inner diameter of the collar, inner diameter of the collar. So which is given by 0.5 times of D, 0.5 times of D, that is 0.5 into D value is, D value is how much? 34 mm. Major diameter of the screw is 34 mm. So if you are going to solve this, then DCI which is equal to, so 17 millimeter, 17 millimeter. Then mean diameter of the collar. So I know the outside diameter of the collar as well as the pin head diameter. Now I need mean diameter of the collar, which is given by DC naught plus DCI divided by 2. So that is DC naught is how much? 68 plus DCI is 17 by 2. So that is, if you are going to simplify this, then you will get 42.5 millimeter, 42.5 millimeter. So other than this, to solve the problem, that means to calculate the torque as well as the efficiency, we need another data for this screw head, that is FC. So coefficient of friction for collar, frictional coefficient for the collar, which is given by FC. So if they are not mentioned this value, then we need to take the collar or screw head material as cast iron, that is hardened steel on cast iron, hardened steel on cast iron. So then we have to look for the table 9.6, which is at page number 137. So when they are not given the FC value, coefficient of friction for collar, so we need to take screw head material as cast iron, that is hardened steel on cast iron. Then we have to go to the table 9.6, which is at page number 137. Then if you check this table, so for this respective material, the coefficient for friction for collar, which is given by 0.147, 0.147. So from this, the step 3 is over, that is design of screw head or collar. Step 1 is design of screw rod, step 2 is design of nut. Now step 3 is design of screw head or collar. Next we move on to the step number 4, that is design of handle, or which is also called as Tommy bar, So this will be the screw rod, this will be the screw head. So this will be the handle, or we can also call it as Tommy bar. So now in this, what we need to calculate? So we need to calculate LH, that is the effective length of the handle. So which is measured from here to the center of the screw jack. So this will be the effective length of the handle, and DH, that is the diameter of the handle, So to calculate the length of the handle, so I am going to take total frictional torque, total frictional torque that is given by T which is equal to torsional moment in screw plus torsional moment in collar. The total frictional torque which is given by torsional moment in screw plus torsional moment in collar or screw head. So, from this we will get the total frictional torque. So, which is given by this T value, total frictional torque, which is given by equation W by 2 times of d2 tan alpha plus coefficient of friction F divided by 1 minus F times of tan alpha plus FC DC plus FC DC. So, this will be available in the data handbook, that is equation number 9.12a, page number 135, page number 135. So, in this equation we know the value of the load, and this one is the mean diameter of the screw, then tan alpha which is also known, which is calculated in the design of screw, then coefficient of friction for screw which is also known, then FCDC, just we calculated the frictional collar friction in screw head design, then mean diameter of the collar in the step number 3. Now, then, so I will call this as equation A, equation A. Then the torque which is also given by force exerted on the handle into length of the handle, that means, so this will be the screw jack, this will be the handle, you are going to exert force on this handle, due to which the screw which is start to rotate. The torsional moment which is induced by rotation of the handle, force exerted on the handle into length of the handle, effective length of the handle. So, I will call this as equation B. In this equation, the force exerted F which is given by force exerted on handle by a person, so which will be around 200 to 300 Newton. For the safety purpose, I am going to consider F value which is equal to 300 Newton. Now, if you can observe this, the equation A and B, the LHS of the equations are same. This will be the total frictional torque, this will be the torque induced due to the force exerted on the handle. Both are same, hence, so we can equate RHS of the equation. So, that is, so equating equation A and B, RHS of the equation A and B. Now, we get W by 2 times of D2 tan alpha plus F divided by 1 minus F tan alpha plus FCDC, which is equal to RHS of equation B, that is force into length of the handle. If you observe this, in this equation all the terms are known except the length of the handle. So, which is given by, now I am going to substitute the values. W which is given by what, how much? 50 kilonewton, that is 50 into 10 power 3 divided by 2. So, D2 is given by mean diameter of the screw, that is 31, tan alpha, that is 0.0616, plus F coefficient of friction of screw 0.14 divided by 1 minus F means 0.14, tan alpha is 0.0616 plus FCDC, so which is calculated in the previous step. So that is FC is coefficient of collar friction, that is 0.147 into DC, mean diameter of the collar is 42.5, which is equal to F into effective length. The force exerted by a person is 300 Newton, then effective length. So the only unknown thing is the effective length of the handle. So now the length of the handle, which is, if you are going to simplify this, then you will get length of the handle, that is 1045.79 millimeter, that is approximately 1046 millimeter. 1046 millimeter. Now we found out the effective length of the handle, the LH value, which is equal to 1046 millimeter. Now what we need to find out? The diameter of the handle. The diameter of the handle. So if you can see this, so this will be the handle. So this will be the axis of the handle. So when you are going to apply a force, that is the force which is perpendicular to the axis of the handle. That is, there will be a bending moment. So the bending moment or bending stress which is induced in the handle. So from this, so the bending stress induced in the handle, which is given by sigma B, which is equal to M into C by I, where M is the bending moment, I is the moment of inertia, C is the distance from the neutral axis to the outer fiber. So if you are going to simplify this, M is M divided by, so taking C into the denominator of denominator, I by C, M by Z. Z will be the section modulus. Here bending moment M, which is given by force into distance. The force exerted on the handle into the distance, effective length, which is given by bending moment. Then Z, that is the section modulus. So I will write it here itself. The section modulus, which is given by pi dh cube by 32. Pi dh cube by 32. So now, so I am going to write this sigma B, which is given by M, that is force into length of the handle, Z, that is pi dh cube by 32. So the 32 in the denominator of denominator I am going to take into the numerator. Now in this equation, the F value is known, that is 300 Newton of force, then length of the handle just we found out, then diameter of the handle, which is still unknown thing, then the allowable stress in the handle, which is also unknown. So to calculate the diameter of the handle, so I need this value, the allowable stress in the handle. So if they are not given the allowable stress of the handle, then we need to take the material for the handle as C40 steel. From that we need to calculate the yield stress. So if you see this here itself, for the C40 steel, the yield stress is given by 328.6 megapascal. Then taking factor of safety as 3, then allowable stress, which is given by sigma y by factor of safety. So that is 328.6 by 3. So finally sigma allowable of handle material, which is given by, if you simplify this, then you will get, so 109.53 megapascal. Now from this we know all the things except the diameter of the handle. So I am going to substitute the values here. Now sigma allowable for the handle material is 109.53, then 32 into force exerted is 300 Newton, length of the handle is 1046, then pi into dh cube. Now diameter of the handle, if you are going to simplify this equation, the diameter of the handle, which is given by 30.78, which is approximately equal to 31 millimeter. Next we are moving on to the design of cup. Okay. Next we move on to the design of cup, that is step number 5. In the step number 1 we design screw rod, in the step number 2 we designed nut, step number 3 screw head or collar, step number 4 design of handle is over. Now we move on to the step number 5, design of cup. Here what we need to find out, so this one D3, that is diameter of cup at bottom, so which is given by, so that is D3, which is given by DC naught. Okay, if you observe the figure, the cup which is placed on the screw head or collar, the outside diameter of the screw head or collar, which is called as DC naught. Outside diameter of the screw head or collar, which is DC naught, so which is placed on the screw head, so which is approximately equal to the diameter of the cup at bottom, which is approximately equal to DC naught. So DC naught value, which is equal to 68 mm, so which is found in the previous step. Next, so D4, that is diameter of cup at top, which is given by D4, which is approximately equal to 2 times of DC naught. So here the cup dimension, which is with respect to the screw head outside diameter, so which is approximately equal to, this will be the D4, which is approximately equal to 2 times of outside diameter of the collar. So hence D4, which is given by 2 times of 68, which is equal to 136 millimeter. Next we have to find here this one, the height of the cup. Which is given by H2, which is approximately equal to in between 50 to 75 millimeter. So I am going to take in between values something like 60 millimeter. So you can take in between 50 to 75 millimeter. I am taking 60 millimeter as height of the cup. Then we need to calculate the thickness of the cup, that is given by T. Thickness of the cup, which is given by T, so which is around 10 to 15 millimeter. So you can take the thickness of the cup in between from 10 mm to 15 mm. So I am going to take thickness of the cup as 10 millimeter while designing cup. And this one, capital D, this distance, so which is already found out. So this one capital D, which is nothing but diameter of pin head. So while designing the screw head or collar, we calculated this distance also, that is the diameter of the pin head, capital D, which is already found out. That is, in the design of cup, we calculated D3, D4, that is then height of the cup and thickness of the cup. So next we move on to the step number 6, that is design of the body. Design of the body. So in this, what we need to calculate, the D1 which is already calculated, that is the diameter, outside diameter of the nut. If you are observe this figure, so this will be the nut, that is D1 from ear to ear, D1, so which was calculated in the design of nut. So which is also known, that is 53 millimeter. 53 millimeter. Then, so D5. So D5, which is called as, so I need to calculate D5. D5, that is diameter of the body, diameter of the body at top, which is equal to D5, which is approximately equal to 1.5 times of D2. 1.5 times of D2. So that is, so on the body, so the nut is mounted. So this will be the D1 value, outside diameter of the nut. So this will be the D2, that is diameter of the nut flange. Diameter of the nut flange. With respect to this diameter, D2 diameter, we are going to calculate this one, that is D5. We are going to calculate this diameter D5. So which is given by 1.5 times of D2. So D2 value is also known. So in the nut design, we found out the D2 value, that is 63 mm. So if you are simplify this, then you will get 94.5 mm, which is approximately equal to 95 millimeter. 95 millimeter. So D1 is known, D5, which is also over. Now we need to calculate D6 and D7. D6 is what? So inside diameter of body at bottom. Inside dia of body at bottom, which is D6. So D6, which is approximately equal to 2.25 times of D2. So D6 value, which is also represented with respect to the D2 value, that is outside nut flange diameter. So if you are going to simplify this, 2.25 times of D2 value is how much? 63. Once you are going to simplify this, then you will get D6, that is 141.75, which is approximately equal to 142 millimeter. 142 millimeter. That is D6 also over. Next, D7. Now this will be the outside diameter of the body at bottom. So this will be the inside diameter of the body at bottom, that is D6. Now this will be outside diameter of the body at bottom. So that is given by outside dia of body at bottom. So which is given by D7, which is represented with respect to D6, that is 1.5 times of D6. D7, which is equal to 1.5 times of D6, that is 1.5 times of D6 value is 142. If you simplify this, then you will get 213 millimeter. 213 millimeter. Next, D7 is also over. Next, what we need to find out? The thickness at base T1, which is given by T1. So T is given for thickness of the cup. T is given for thickness of the cup. I am using T1 for thickness at the base. So thickness at base of the body, which is given by T1 which is given by 2 times H, 2 times H which is nothing but thickness of the nut flange, which is given by H value, while designing nut, which is also known, that is H value which is equal to 16 millimeter. If you are going to simplify this, 2 times of 16, that is 32 mm. Now, so T2, so T1 is over, T2, that is thickness of the body. Now T2, that is thickness of the body, which is given by T2, so which is equal to 0.25 times of major diameter of the screw, 0.25 times of major diameter of the screw, that is 0.25 into major diameter of the screw is how much? 34 mm. So 34, if you are going to simplify this, you will get 8.5 millimeter. So I am going to take the whole number, that is 9 millimeter. So from this we calculated T1, D5, D6, D7, T1 and T2. So we are left out with height of the body. So height of the body, which is given by is given by length of the screw plus clearance. So this height of the body, which is determined based on length of the screw as well as the clearance length of the screw, which is found out in the design of nut stage. So length of the screw is how much? 399 millimeter. Then clearance, for the safety purpose, we are going to take clearance of 50 mm. Then height of the body, which is given by 449 millimeter. So height of the body, which is also found out. Next we move on to the step number 7 and 8, that is to calculate the efficiency of the designed screw jack and checking for overhauling condition. So now we move on to the step number 7, that is efficiency of the screw. So in step number 1 we design the screw, step number 2 design nut, in step number 3 we design screw head, in step number 4 design the handle, in step number 5 design the cup, step number 6 we design the body. So the designing of these things component, which is not enough, so we have to check for the efficiency of the screw and check for the overhauling condition in step number 8. To calculate the efficiency of the screw, so I am going to use this equation eta, which is given by d2 times of tan alpha divided by d2 times of tan alpha plus f divided by 1 minus f tan alpha plus fc dc. So which is available in the data handbook. Equation number is 9.12b, page number 135. So I am going to substitute the values to calculate the efficiency. So d2 tan alpha, d2, that is the mean diameter of the screw, d2 is 31, tan alpha, which is given by 0.0616, 0.0616 divided by d2, that is 31, times of tan alpha, that is 0.0616 plus f, that is coefficient of friction in screw, which is given by here 0.14, then 1 minus f is 0.14 times of tan alpha, that is 0.0616 into this one. plus FCDC, that is coefficient of friction in collar and mean diameter of the collar. So coefficient of friction in collar, so which is 0.147, which is calculated in the step number 3. Then diameter of the mean diameter of the collar is 42.5. So if you are simplifying this, then you will get 0.1521. 0.1521. If you are going to multiply with 100, then you will get in percentage, that is 15.21%. The efficiency of the screw, power screw, based on the design parameters, which is equal to 15.21. Next we move on to the step number 8, that is check for overhauling condition. So this will be very important in the design of screw jack, just because when you are going to lift some load, then the screw jack has to be hold that load in that place for some time, unless we are going to apply some effort. If without applying any force, if the load is descending on its own, then which is called as overhauling of screw. The preferable property for the screw jack is which has to be having the self-locking property. That means the load has to be sustained for some time unless we are going to apply the force. Which is called as self-locking property. Now, which is given by this equation, which is available in the data handbook 9.12c, page number 135. Now I am going to divide into LHS and RHS. That is tan alpha, which is greater than or equal to F D2 plus FCDC divided by D2 minus F into FC into DC. That means when tan alpha, which is equal to RHS term, this will be RHS, I will call this as LHS. When LHS, which is going to equal to RHS, or when LHS which is greater than RHS, then the screw overhauls. That means the load which is going to descend on its own. So let us check this property. So LHS, that is tan alpha, which is given by 0.0616. This will be the LHS value. Now RHS, which is given by FD2 plus FCDC divided by D2 minus FCDC. If you are going to substitute the values, then F is coefficient of friction for screw, that is 0.14, D2 is mean diameter of the screw, that is 31 mm, plus FCDC, that is frictional coefficient for collar, that is 0.147, then mean diameter of the collar, is 42.5 divided by, so D2, that is 31 minus F 0.14, FC 0.147, DC 42.5. So if you are simplify this, then you will get 0.3514. That means, now observe the LHS and RHS. From this you can find LHS, that is 0.0616, which is less than RHS, that is 0.3514. LHS is less than RHS. So based on the design properties, so we got LHS which is less than RHS. So from this, if the screw the condition for overhauling of the screw, that should be LHS should be greater than RHS or LHS should be equal to RHS. But we got LHS is less than RHS, that means the screw which doesn't overhaul, then which is having self-locking property. So the screw which is or no overhauling which occurs in the screw, then we can conclude that it is a self-locking screw. Self-locking screw. So the load which doesn't descend on its own. So from this we can conclude that it is a self-locking screw. So now this will finishes the problem, that is the complete design of screw jack. From the starting from the step 1 design of screw rod, step 2 design of nut, step 3 design of screw head or collar, step 4 design of tommy bar or handle, step 5 design of cup, step 6 design of body, step 7 checking calculating the efficiency, step 8 checking for overhauling condition. So in the examination they will frequently ask for design of screw rod as well as the nut. If in case they are going to ask other things, that is like tommy bar or cup, so these are the steps. These are the steps to be followed to design the tommy bar or cup or any other components in the screw jack.